So as far as the proof for this, even though maybe you won't learn too much out of doing it, you're trying to show that integral from a to b of, use the same notation here as we have, that's f of b minus f of a. Now we already looked at graphically when you have antiderivatives, right? When we had an antiderivative of x squared, it was x cubed, a third x cubed. But it could have been plus 1,000 or minus 7 or whatever, right? It could be anything, as adding any constant here, right? Any constant, okay? It doesn't matter which one you use, all right? So if you're trying to do this, you can say that we know that there has to be some kind of antiderivative, like this function has to have an antiderivative, okay? This is any, f is any antiderivative. Let's say f is any antiderivative. It's not just a single one, it's any antiderivative of f. But let's say g is some specific one, right? So in other words, though, you need to realize that f of x equals g of x plus c, plus some constant, right? They're only separated by a constant. So you could say f is any antiderivative, and it's hard to talk when you talk about something like that. But this should be this is the same as minus g of a, right? Okay, so that's like whatever one we pick, we're just having to shift it by a constant there. So if you simplify that, obviously it says g of b minus g of a. So that's the specific one that we happen to be using. If you write that out for our formula here, if we know that, like, from the first part of the Fundamental Theorem of Calculus, it says that this formula here, this thing has to exist. A to x of little f. The first Fundamental Theorem of Calculus, I guess I should have put this down below here. I can't write it here. The first part says that's an antiderivative, right? Because this is what we need now. We need an antiderivative for that function. This is an antiderivative. First part of the theorem says you can use that. Even if you don't know what the function is, you can use that. So if we want g of b, we can just write integral from a to b of this function. And for the second part, I need to make this smaller and get it out of the way. And for the second part, we can say integral from a to a, right? Put the value we're looking for. This says g of x is integral from a to x, then g of a is integral from a to a. Keep that separate. What do you know about those two things, though? Second one's 0, right? Minus 0. So you got integral from a to b of f of t dt. It doesn't matter what the variable is there, right? And I guess, whoops. This could have easily been t here. It doesn't really matter what the variable is as long as that one matches that one, right? Does that make sense? So we've got down to the point where we have, I'll move this. We got down to the point where we have that integral from a to b of f of x dx equals integral from a to b of f of t dt. It doesn't matter what variable you're using there. We've already seen that you can just use a different one if it's more convenient. That's it. Okay. Now I don't know how much you get out of that proof. It seems like you're just proving it by. You need the first part in order to prove this. You need to know that there is an antiderivative that you can write with an integral sign like that. Okay. So hopefully maybe that makes some sense to you, and you might find it useful at some point. But the thing you're going to use it most importantly for is just evaluating integrals, right? Knowing that you can work out the value of an integral using antiderivatives.